Alright, so how to I'm doing this now for the second time. So I am going to run through this real quick again so I can get this uploaded. So we're going to be using Python to solve the problem, and we're going to be doing numerical calculations. So we're going to want to use the NumPy library. So we'll import NumPy as we'll use NP as the standard name. We're going to be solving the differential equation, and Python has a package called SciPy that has a module called integrate, and inside that there's a solve IVP function. So we're going to want to import that function. So from SciPy dot integrate import solve IVP. And then SciPy also has a module called optimize, and we're going to want to import the root function because we're going to end up having to use that since we don't know the initial conditions. We don't know all our initial conditions, as we'll see later when we try to do the solve IVP. And then after we get done solving the differential equation and we have our solution, we're going to want to plot that. And so we're going to be using Plotly. So we want to be able to make a subplot, so we want to import that function. So from Plotly dot subplots import make subplots. And I don't like the default template that Plotly uses, so I will change that, and I'll just have to do import plotly.io as pio, and then we can change the template default to my template of choice, which is Plotly dark. And since we're dealing with mass transfer and concentrations, the way we're talking about concentrations of the water vapor has to do with the partial pressure of water vapor. And so we need to be able to calculate the partial pressure of the vapor pressure of the water as a function of temperature. So what I have imported right here, I just have this PV function. All it is the Antoine equation, which allows us to calculate the vapor pressure of the water at any inputted temperature T. So I'll go ahead and run that. And then here I just have all the parameters for the problem. So we have the heat transfer coefficient. This is something that you would have to be obtained experimentally. In this case, it was just given to us. It's 10 watts per square meter Kelvin. We're going to be doing a lot of using the ideal gas law a lot, so we're going to want the ideal gas constant, the universal gas constant, so we have that right there. Density of the air, and since we're dealing with energy transfer through just energy transfer, we also have to have the specific heats of the air, the water in the vapor form, the specific heat of the water in liquid form, and then also the enthalpy of vaporization, since the water is going to be evaporating. And then we also have the mass transfer coefficient in terms of the heat transfer coefficient. This is just the Lewis relation, which we talked about in the last video. And then we also have this A here is characteristic to the packing in the column. So this is 5 square meters per unit volume. So for every cubic meter of your cooling tower, you'll have 5 square meters of surface area. So that is the surface area of water then that will be exposed to the air. And then I also have molecular weights of the water and air, and we also have the velocity of the air coming in. So that's how would we measure in real life? How would we measure the amount of air coming in? We would use like a pitot tube, and that would give us velocity. And then we also were given the liquid flow rate, so we have 0.5 kilograms per second per area coming in, the water, liquid water coming in. And then we also have the total pressure. And the height of the column of the cooling tower is 20 meters. And then we also have the temperature of the water coming in, the temperature of the air coming in. So the temperature of the water is coming in at 70 degrees Celsius, the temperature of the air is coming in at 25 degrees Celsius. Just remember that we're dealing with a countercurrent heat exchanger essentially. So the air is coming in, the water is coming in at the top, going down the cooling tower, and the air is coming in at the bottom and coming up the cooling tower. And the way we set our positional coordinates, that's z equals 0 at the top. And so the water comes in at z equals 0, and the air comes in at z equals 20. And then the air would leave then at z equals 0. And it's just important to remember when we go to solving this differential equation where we have to have initial conditions. And then we also have the mole fraction of air, of water in the air, of water vapor in the air. So that's just, we're giving that it's 50% relative humidity. And so that's 50% of the max amount of water vapor that the air can hold. And the max amount that it could hold would be the vapor pressure of the water at the temperature of the air. So that's, we have the Antoine equation right here. We're evaluating that at the temperature of the air feed. That gives us, so that's 50% times the vapor pressure of water at the temperature of the air feed. That would give us the partial pressure of water vapor in the air feed. And then if we divide that by the total pressure, we then get the mole fraction. So have the gas flow rate of the air. So we have the velocity of the air. How would we convert that, the velocity of the air, into mass flow rate? We would have the velocity of the air coming in times the area. That would give us volumetric flow rate, and then we'd multiply by the density to get our mass flow rate. But we want our mass flow rate to be in units of per unit area, so we'd also have to divide by area. So we'd get rho, the density times velocity times area, and then we'd divide by area. So we just get the density times the velocity, and the density we use the ideal gas law, so we have PM over RT times the velocity, and that would give us our the mass flow rate of air per area. And so we want to solve our differential equation, and when we use solve IVP, we need to input a function into solve IVP that returns the right-hand side of our differential equation. So we will define that right-hand side of our equation. We'll define that as a function right now. So we'll call it dy dt wtg. So that stands for like derivatives of the mole fraction, derivative of temperature of water, and derivative of temperature of the gas. And remember that when you put this into solve IVP, it wants the first function, the first parameter argument to this function to be your independent variable, so that's c. And then the second would be our dependent variable, so we'll just put that as a parameter v. Dependent variables are y, tw, and tg, so we will just say y, so the mole fraction of water, and then we have temperature of the water, and then we have temperature of the gas. That's just equal to our dependent variables, which we said v. And then I have this, so this right here is just the right-hand side of our differential equation that we derived on paper in the previous video. So I just copy and pasted it. I already had it down before, just so it would save time and I wouldn't have any errors typing. So this is what we have, so we would want to return the right-hand side of the differential equation. So we just want this function to return dy dtw and dtg. But the problem is that the way I wrote this down, there's some things that are not defined. So what is not defined? This m here in the dy equation, that is the average molecular weight of the air-water mixture. So we can write that as total mass of the water and vapor. That's just mass flow rate of the air plus the mass flow rate of the water. That will give us the total mass and then divide by the number of moles. So instead of it being mass flow rate of the air, we want to divide that by the molecular weight of air, which I'm just making sure my variables are the same, okay? And then we want, instead of the mass flow rate of water, we want the molar flow rate. So instead of the mass flow rate, we divide it by the molecular weight of the water, and that will give us the moles. So it's the kilograms over moles. That gives us the average molecular weight. So what else do we need? We don't have the flow rate of the water. We can say though that the total flow rate would be the sum of the flow rate of air plus the flow rate of the water. And the flow rate of the water, if you think about the molar flow rate of water over the molar flow rate of the air, that would be equal to the mole fraction of water vapor times the total gas flow rate divided by 1 minus the mole fraction of the water vapor, because that's the mole fraction of air, times the total gas flow rate, and then those would cancel out. So you're left with, you have mole fraction divided by 1 minus the mole fraction. So that's the mole fraction of water over the mole fraction of air, which is just 1 minus the mole fraction of the water. And then we have, and I would carry everything. I'm doing this in my head, so I would carry this stuff from the left-hand side and simplify it so I get the gas flow rate of the water. So I would get gas flow rate of the air on this side, and then I would have molecular weight of the water, and then yeah, so yes, that comes out, and then molecular weight of the air. So that's the gas flow rate of the water, and then this is our total gas flow rate, and then we have molecular weight, average molecular weight, and then we also need like the average specific heat. So which down here I have that as CG, so it's just gas flow rate of the air times specific heat of the air plus G water times specific heat of the water vapor, CWG, and then that's all weighted by the total gas flow rate. So basically what I'm doing there is I'm taking each of the specific heats and then weighing it based off its mass fraction in the flow. And this should then, okay, cool. So now if we go to do solve IVP, we'll just go about this naively at first. So TG, we want to solve it from 0 to the height of our column, right? change the method to Rudel method. Sentence output equal to true. And we also need initial conditions. And so what are the initial conditions? This is where z equals 0. So that's z equals 0 is at the top, so that would be the mole fraction of water vapor in the air that's exiting. So that's y exit. Then what about the initial condition for the temperature of the water? That's the temperature of the liquid water. We already know that. That's the temperature of the water feed. So that's fine. And then temperature, initial condition for the temperature of the air. That's the temperature of the air exiting, because the air exits at z equals 0. So T air exit. And so we can't solve this because we don't know those initial conditions, but we know the conditions of the air stream at z equals 0 at the end. So what we're going to do is we're going to define a function that's going to try to find, that is going to find the temperature, the conditions of the airstream at the exit. It's going to find that correct initial condition that satisfies the conditions at the other side. So we're going to use the root function. So we want to make a function that we want to be ultimately be equal to 0. So I'll just go define, I'll call it funny function, whatever you want to call it, and that's going to take in some parameters v2. So what are these? We want it to take in the exit conditions of the air. So it would be y exit and temperature air exit is equal to v2. And then we would want to solve this. So the solution equal to this. And then what would we want to return? We want it to solve the differential equation at these exit conditions. And based on that solution, we're going to see what solution that it came up with. We're going to see at z equals 0 what the mole fraction of the water vapor is and what the temperature of it is. And then we're going to take that and subtract it from what we know it is. And that way, when we do the root function, it will be finding the exit conditions that make it 0 at the other end. So when I put this as sol, I'm going to just go ahead and evaluate the solution at z plot, which I will have to define up here. So each time it solves it, you're going to be getting this sol variable is going to be giving you the data set of the solution that it came up with every single time. And this will allow us to be able to extract later without having to go ahead and solve it again. We'll just save time, so we'll do a linear separated space, and so that's from, these are z values, so some 0 to 20, and we'll say 21 points between that, so they're all linearly spaced. So I'll go ahead and run that. So it's going to take these as z plot, and so what this sol variable is it's an array that contains 3 arrays. The first array is the mole fractions of water vapor between 0 and 20 meters down. And then the second array is the temperature of the water between 0 and 20 meters down. And then the third array is the temperatures of the water, of the air, of the gas between the top of the tower, 0 to 20 meters down to the bottom of the tower. So we want to take the mole fraction that the solution says it is, the mole fraction at Z equals 20 at the bottom of the tower. We want, what does the solution say that is? We take so the mole fractions is the first array, and we want the last value in that array, because that will give us at Z equals 20. So that we want to subtract that from what we know the mole fraction is at that location. And then we also want to do the same thing, but this time for the temperature, which temperature of the gas is the third array. So index of 2, since index starts at 0, and last value just like that. And then we want to subtract that from what we know the temperature of the gas feed to be. Just like that. And now we should be able to do the root function. So this, the function we're trying to find the root of, that's the function we just defined, funny. And then we need guesses for it. So what do we think the mole fraction at the exit is going to be? So just remember, exit, so that when the air exit, what's the mole fraction of the water going to be? So what is the mole fraction? Well, it comes in at YA feed, and we know that water evaporates, so there's going to be more, the mole fraction is going to increase, so let's just put a guess as to like a 10% increase. And then what about for the temperature of the air exiting? So the temperature of the air feed, it comes in at 25 degrees Celsius, but the water comes in at 70. So you expect the temperature to increase by the time it leaves the cooling tower. So let's just say an increase of 5 degrees Celsius. And let's see what we get. The solution converged. So at this point, we have the solution to our differential equation. Well, first of all, you should see that x down here, this is what the mole fraction at the exit is, and this is the temperature at the exit. And now we want to graph our solution, but we want to be able to grab the solution. So the solution is right here in our function. It's in the local scope. So if we want to be able to get it, access it from the global scope, we need to declare it as global. And this will just allow us to grab the solution since it's already right there. We could go and solve IVP with the initial conditions that we now know, but this is just easier. So we'll declare solve variable as global scope. And let's just see, now can we grab it? And we can grab it, so there we go. So now we want to just plot, so at this point it's easy. We'll do make subplots, and we're going to have 3 different plots, so we're going to graph 3 different, there's going to be 3 rows, so we'll say rows equals 3, columns, there's only going to be 1 column, and then we can do add a scatter plot. So we're going to graph the mole fractions first. So the x-axis, axis is just the z plot values we have. The my values is going to be the mole fractions we had. So that's solution sol. It's the first array. Yeah, so the first one. And then we want all of those values. So it's right here, all of these. So we just represent that by a colon. So that grabs all of those values. We can even, let's make this look neater real fast. We have to say which row that's in. So it's going to be the first row, and it's going to be the first column. And we'll even give this a name. It's going to be just mole fractions of the water. Now we just have to do the same thing with the temperature of the water and the temperature of the gas. So make it easy, just like this. So instead of it being the first array of this, it's the second one, and we'll graph this in the second row, and this is the temperature of the air, or temperature of the water. That's temperature of the water. It's temperature of the water, like that. And now we just want to graph the temperature of the air. So we'll graph that in the third row, and we'll call it temperature of water. And we'll see what we got. And this is our 3 graphs, all in one plot, in one figure. And we can even just take this and update the layout to make it look nicer. We can change height to 800, and width we'll say is 600. See if that makes it look a little bit better. Yeah, that looks nicer. And yep, so there we go. We solved our differential equation, and we plotted the solution that we got. Thank you for watching.